So kind of an agenda. We're going to talk about what we're going to talk about. We're going to describe some terminology so we don't get too confused. We're going to talk about common problems, and then we're actually going to build a web app and talk about a few key areas that I've seen in my experience always be the main bottlenecks in a web app. Actually, let's first define web app. Typically, I define web app as any kind of application that sits facing a user, which generally has some kind of data stored behind it, so some kind of data that's backing it, and that data is generally very dynamic. Also importantly, the difference between performance and scalability, so there's no confusion. Performance generally says my request takes what's called 5 seconds. It's a really slow request. Scalability says I can handle 10,000 requests concurrently, and they will continue to take 5 seconds per request, and I can continually scale that out so it's always 5 seconds per request. We're also going to actually talk about scaling more than just the requests per second you have. We're going to talk about how you can scale your code base better and manage it better. Another key concept we'll go over in this is sharding, which generally just means splitting up your data by some kind of predetermined key. So if you have data that's generally bound to a user, maybe you split it up by that user ID. We'll also talk about denormalization, which generally is maybe you have counters and you need to know the number of people that are in this room. So you increment and decrement a counter, which is actually a denormalized state because you also have a full list of the users in the room at any given time. All right, so first up, we're going to talk about common bottlenecks and problems, I guess. Database is generally your issue. Almost everything we do, we see improvements to the database always bringing us more scale and more performance. Sorry. You'll also tend to find that when you're building for scale, you're also achieving performance at the same time, which is a nice benefit, I guess. Caching and validating that cache is also pretty key and important. We cache very, very heavily, and it works out fairly well until you start having many areas where you're caching the same kinds of data, and some areas where you're caching the exact same objects in the data, and then you need to invalidate that. And that can become a very, very tricky problem, which is also one of the issues when jumping into caching anyway. Which is also, as Mark was talking about, why things like Postgres are great, because they scale very well. And Disqus has been using Postgres for 3 years, and we do have ridiculous hardware, but we have a single master server that stores a good 98% of all of our data. And the other third big one is a lack of metrics and tests, and we'll cover this a little bit, not too much today. You get another talk tomorrow morning if you're interested in metrics and testing and deployment and things like that as well. So we're going to build a Twitter clone, because everybody likes Twitter clones, and everybody knows what Twitter is. And it's honestly a very simple app, very straightforward app. So what do? We're going to pick a framework, because there's no reason to not use a framework in Python where there's 1,000 frameworks. And then we're going to package our app, and packaging is key. Packaging lets you deploy much easier. It lets you repeat your deploy, which actually scales your deploy, and it makes everything about working with your application better. If you have new people joining your team, if your app is properly packaged, it should be easy to set up. If you have an open source project and somebody's contributing and you package your app correctly, it should be easy for them to set up. It should be easy for them to run the tests. It becomes very, very important, even if you're just working by yourself, when you distribute your app and things like that. Also, we want to solve problems, and by that I mean we don't want to try to solve non-existent problems. We don't want to scale a system that nobody's going to use. We don't want to use MongoDB as an example because we think it might be cool. We're going to use things that work, and we're going to use things that we know work. And it really just makes sense when you consider it. And invest in your architecture. And by this I mean invest in kind of the API that powers everything, the general way you built and structured your app, your code, your databases, all of this. It's been pretty important that we've seen to always plan ahead. This doesn't mean take a week or a month to determine what the best way is to do something. Generally, you can like I tend to sketch out things in code if I'm building a new system, and then going from there I can kind of see how that's going to play, and I can see where it's going to be slow. So first thing, we're going to pick a framework, and we're going to use Django. We're going to use Django primarily because Discuss uses Django. Discuss is very, very large, you could say. We're one of the larger Python apps, possibly the largest Django app. We do about 3 billion page views a month. I'm not sure what our last peak is. When we gave a presentation at Python US, and at that time we peaked at around 25,000 requests a second to the Python web servers. And we've grown very fast. We grow about 20 to 50% sometimes every single month continuously, which means scaling is very important for us. And so Django, again, it's fast enough. If we can use it, there's a lot of other big companies using it. Mozilla uses it very heavily. Anybody can use it. Most frameworks are going to be completely fine nowadays. They've matured. If they haven't, nobody's going to use them. Nobody's going to recommend them anyways. Django comes packaged with everything. They call this batteries included, which is actually very nice. I was talking to Armin Ronecker, the creator of Flask, the other day about my introduction to Flask from Django. And having to do all of the heavy lifting myself, find all the components, build the components, is surprisingly tedious. And Django gives you a lot of that for free, which is very nice. Django is also very well maintained, meaning there's new releases. I think it's like a yearly release schedule, maybe quicker than that. They're at version 1.3 right now. They're working on 1.4. They released 1.2 less than a couple years ago, and it's been iterating fairly well. It's become much better over the years. It's become more stable and faster. The APIs have matured. It's also very, very well tested. It has insane amounts of tests. They put a lot of effort into it, which means it's going to be stable. You don't have to worry about, is this going to work when it goes into production? It's used, like I said, by a lot of big companies like us, like Mozilla. There's a bunch of others that I can't name off the top of my head. And also, documentation is very, very good with Django. I actually learned Python by learning Django through the documentation. I came from the PHP world 5 years ago, and it was honestly a fairly easy transition. I didn't learn how to scale Python through those tutorials, but over time, learned from the mistakes, and all in all, very happy with Django. So, let's move on to packaging our app. So packaging in Python is kind of one of my pet peeves lately because there's too many ways to do it. There's too many ways to do it, and everybody's trying to solve the same problem, and nobody really has it solved. I don't have an answer for it, but I've decided to just use setup tools and distribute because generally it just works for me. There are people that dislike it. I'm aware there's some reasons to dislike it, but it generally works. And the reason I would choose it over things like distutils is because it gives you access to very useful utilities, like the develop command is pretty awesome. And you can do things like with pip to mock the develop, but I've been told there's some issues with it. So we have a basic package here. We're naming it Tweeter, and we're requiring Django. And this is actually pretty important. We freeze all requirements. So, and by that we mean we specify precise versions for all requirements. And doing this gives us a very, very stable build, a repeatable build. It also means that when we do things like deploys, we don't have to upgrade dependencies just because they're updated. You can also specify something called tests require, which I'm not entirely sure works all the time. I've tried to adopt it, which is very nice. So if you set up a PyTest and you define your collector and everything in here, it will actually install dependencies there as well, which also makes it easy for anybody who's coming in to use your project. And then there's a simple standard test command they can just run and it works. So once we have a setup.py, a basic package for application, it makes things very easy. You can use a virtual env, clone your repo, and then you run like a develop command, and it should pull in everything. And that's been key for us to make setup of like a new team member's computer something very, very painless. And we actually use this this with tools like Vagrant, which is a virtual machine, to make it really easy to install services like Redis or Postgres or Rabbit, because we actually have a fairly complicated stack once you get to the higher tier. And another important tool that will help with this is Fabric. If you're not familiar with Fabric, you're likely familiar with Capistrano, and if not, it's a deployment tool written in Ruby that basically gives you easy entry points to running like SSH commands on remote servers. And the reason this is very useful is because it allows you to do things like deployment and to local deployment, I guess you could say, very consistently and on many servers. So for example, you can, with the multi-host or multi-processing or some package in Fabric, you can actually execute like commands on many machines. And potentially you could run those in parallel, or you could roll it up exponentially to do more and more machines. So the databases. And I said databases first. And when I was originally writing this talk, I started building the app. And I realized everything I wanted to talk about eventually boiled down to how we were accessing our data. And I say databases, I don't mean just Postgres, I mean any kind of data store that you're going to use. So they're usually the most important part. Unique consistency in almost every single system. You can have something on top like Memcache that doesn't have to be consistent as long as you can rebuild it from some kind of point. They're a very, very common bottleneck, which also means they're an awesome bottleneck to improve the performance on because they affect everything. Especially with things like SQL databases, they can be very painful to change, especially if you use MySQL. MySQL doesn't like letting you change the schema once you grow to a certain size without taking the server down. And they can be generally hard to scale. And that means hard to scale once we get beyond one server. There's things like master-slave, which introduce more problems like replication lag. And if you hadn't had to deal with that, pray you never have to. It's the worst thing ever. There's no good solutions for dealing with it as well. So what we try to do is actually avoid having to worry about if replication lag exists, and we do that by pushing state to various machines. So if so our product looks, actually let's take Twitter. Let's say you have a timeline which shows all of the tweets from people you're following. And it's easier when that tweet happens to push it into some kind of cache rather than reading from a read slave and writing to the master where you may or may not have a consistent state of the data. So let's dissect our tweet. This is a picture of the Age of Conan sword. I was asking for an interesting tweet to put up here, and this is what somebody gave me. So we have the author of it. We have a picture and some various things about them, but we're not going to worry about the user model. We have the tweet, which is the text, and we have like a date time, and there's some other various bits that we're also not going to worry about, like the application, which is TwitPig down here at the bottom, and some other actions. So generally what I do is I build out a model, and this is a Django model if you're not familiar, and it describes precisely what your database looks like. If there are fields in your database that aren't present in this model, it'll work. But if there are fields in this model that aren't present in your database, it won't work at all. So, like I said, we have the bare basics here. We have the user, we have the message, we have the database posted, and there's also the concept of parent-child relationships. So if you're replying to something, you also have relationships between users. So it's like if I'm following you, we need to report that somehow. So given that, let's take like the public timeline, and the public timeline is literally like you can view everyone's tweets everywhere. So this is a simple way to do it in SQL is you just select from the table with no conditions and you order it by the date and you limit to however many results you want. This works generally well as long as your data fits on one machine. If your data doesn't fit on one machine, you can't just do a simple query to get that data. You have to actually do something like a MapReduce job and spread it out to various machines, get those back, and then filter down to 100 results. This also generates very, very large indexes. Like in this case, we would need an index on date, which can get very, very big. And it's also very important that if you're going to be routinely querying things like this, that those indexes fit entirely in memory. If they don't, you're going to hit a lot of issues with swapping, and as soon as you start swapping, your database is no longer fast. And if it's no longer fast, it's no longer going to scale. The nice thing about this is it's very easy to cache and it's very easy to validate. It's a single cache key for every single user. Every time somebody makes a tweet, we can just push that into a cache and it's a shared state for everyone. And we move on to the following timeline, which is if you visit Twitter at your home, it shows all the tweets from people that you're interested in. This is a little bit more complicated because we actually need to join the data. We need to say, I want tweets that are from these people. And those people could be one or it could be a million people, and that gets very complicated. So there's other issues with this in the sense, or in partitioning logic. Generally, if you have a lot of data, let's say those tweets and your users wouldn't fit on a single database server. Well, you can easily separate your tweets from your users and put them on different machines, which gives you a very easy win. And we generally refer that as vertical partitioning. Given a query like this, we can't actually do that because we're doing this required join to actually get the tweets that are from these people that I'm interested in. And it's also kind of annoying to deal with caching on this. For example, if I push to your stream that's a cache just for you, and then this user decides to delete their tweet, that should be pushed out immediately to all streams that are part of that user. That means we have to invalidate all these keys. We have to be aware of all these keys in every single situation that has these potentially changing objects in it. So we're going to introduce materialized views. The concept of this has existed for a long time. Certain databases actually give you this for free. MySQL has non-materialized views, which means you can create a table, which is a view of a query, but that query is run every single time, which means you can't index things, which means they're inherently slow. Postgres, I think, has views as well. I'm not entirely sure. I've never used them. As far as I'm aware, they don't have materialized views. I think the nicer servers, like Oracle and MS SQL, I believe, have full materialized views, which will give you indexes and give you very, very fast queries. So we're going to go with this in mind that nobody has the money for Oracle. And we're going to build a materialized view. So this is a very bad way to do it. We're just assuming we have a single process and we can store this in memory. We've got a public timeline, which is a list. Every time a tweet's created, we insert it into the list. And then to get the latest, we just pop off we pull out the last 100 or whatever from that list. So a better way we can do this is with Redis. And I discussed we use Postgres, we use Redis, we formerly used MongoDB. We've tried a bunch of solutions. The only ones that have stuck are Postgres and Redis. We're fairly happy with Redis. At our scale, there's issues with just about anything, Redis included. But it's very nice because you have a lot of cool data structures. And if you're not familiar, one of those is called a sorted set. And basically what that gives you is a sorted list with a float value for a score. And you can insert values in there. All operations are very predictable. They're all log and n. And it's generally fast. Storage size is kind of iffy, we're unsure. But even for smaller sites, you can scale out this way to make the system as a whole scale better. You generally don't need 25,000 requests a second to scale your system. You can scale a system that gets 100 requests a second and get great improvements in performance and manageability. So given this, we have a timeline class. We instantiate a Redis connection. It has three methods. It has add, remove, and list. Add basically writes a tweet. It just writes the tweet ID, and I'll talk about why, into the sorted set, and it gives a score, which is actually the Unix timestamp of the tweet. And the reason we set that is so when we order things, we're going to get most recent, which are sorted by the timestamp. It has remove, which simply removes it from the set, and then it has list, which returns the tweet IDs. So one issue with this is, going back to Twitter, if you've ever used their search or something, you'll know that you cannot search past 7 days. In your own personal timeline, you cannot see past, I don't know if it's a fixed number or a fixed time, but you can't see all tweets forever. Facebook, same thing, you can't see all data forever. They have the data in some kind of maybe relational database, but in the views that you're given access to, they don't allow you to view that data. And the reason is it's very hard to scale the never-ending long tail situation. So one thing we can do with that is we can actually do some kind of cleanup. And we built a truncate method here, and what this does is actually finds any tweet that's older than 30 days. So it creates a Unix timestamp that is 30 days ago, and it deletes, or it runs this remove by score range query. And it basically just says anything that's less than this, remove it from the table. Works fairly well. Again, this isn't a log and operation, and if you keep your data small, it's going to be very fast. Even if the data is not very small, it's still going to be very fast because Redis, just like MongoDB and everything else, sits in memory most of the time. So now we actually need to scale Redis. And we need to scale this in the sense that we don't just need one person's view, we need many views, and maybe one machine's not enough. Or maybe eventually one machine's not enough. And if you know eventually, you can actually say that eventually one machine is not enough. It's pretty easy to actually plan ahead and to make it simple now, but to make it simple later. And we do this by sharding right off the bat. And we have a predefined key in these cases. We have like a user ID. It's my stream, so I'm going to have tweets just for me, so I can keep out a user ID. If we're going to do 1,000 entries, for example, then it's predictably scalable, and that we have 1,000 entries per user, and we know that each machine can hold this many users' data. So to do this, we're going to use something called Nidus, which I'll talk a little bit more on the next slide. And we're just going to create a cluster of 64 hosts here. And we do this a very simple way, which isn't a great example, and we just set the DB number in Redis to 0 to 63. And the DB number is basically a way to identify the database it's using. Ideally, you wouldn't do this and you would use virtual machines, and you would set different host names instead. So Nidus is something that we had an internal project that we were building out to actually do this exact thing. And I needed something for this talk, so we open sourced Nidus. And you can get it on GitHub/discuss/Nidus. Basically, it's a generic connection manager that lets you build clusters and routing logic inside of those clusters. We've packaged in a Redis backend, which is more or less just a proxy to the Redis connection. And we've also started building out some kind of draft code that's in there to proxy Django database connections, so we can have like a core routing layer that does all the routing, and we don't have to build up a bunch of connections inside of Django itself. So in this example, we're creating a cluster. We specified it in the backend, which is Redis. We specify the router, which the partition router that it gives you for Redis that's built in literally just does a hash on a CRC32 hash on the key, and it does modulus on the number of hosts in the cluster. And basically, that gives you predictable hashing throughout the cluster. It doesn't give you availability in the sense that it's not writing your data to multiple places. It's not doing consistent hashing. And that's a whole other problem that you'll need to solve. Redis, in this example, Redis does have master-slave support. I'm not sure if we use it. I'm not sure how many people use it. You could get availability in that sense. Anyways, and then if you run a command like this ether command, it implicitly knows that the first argument to everything is going to be the key, so it can map that to the cluster. If it doesn't have a key, it runs implicitly on all nodes, which is why things can be bad in this situation. If you run a flush DB, which is like a truncate, everything gets wiped on every single node. We've also built in some things so you can pull out a connection based and passing it in the same logic that you would pass into your router. And so you have a hard connection to Redis, and you can get the precise server you want. So given that, what we've just described is also known as horizontal partitioning versus previously vertical partitioning, which is where we separate our users and our tweets. We also talked about how we created 64 of these nodes, and they were on the same machine, which is extremely valuable because as soon as you need to grow, you can take one node and put it on a new machine. Generally, the way we've done that is we have something that looks like this. Let's say we have a master and a slave standard SQL setup for availability. And then we have a Redis server. And we have, let's say there's 64 VMs on here. And we whenever we launch a new product, we immediately jump to shard, especially with Redis, we immediately jump to sharding right away. And we just do as many nodes as we can manage, basically. And 64 is a nice round number. So then, as you grow, we can split users into their own database. We can split tweets into another database. If you need some kind of controller, you can split this master database that has... In Postgres, you can actually have different indexes on different... between your master and your slave. You might be able to pull it off in MySQL, but I'm not sure how well it would work. So given this, we can have a master with absolutely no indexes but primary keys, just as this backup data store. All of our data is here. If we need to figure out if something references something else, or for some kind of odd analytics queries or something like that, we can use a data set like this. And then we split up users and tweets into their own databases, which gives us some leeway in data size and index management. We've also now split Redis into two nodes. We've taken half of the shards and we put them on one physical server. We've taken the other half and put them on another physical server. And we can keep doing that up until the max number of shards. Once we hit the max number of shards, which is 64, and no longer can we buy ridiculously cheap high-end hardware, which will never ever happen, because hardware generally scales as fast as we have. So given if you have 64 machines, by the time you fill up those, maybe you get a terabyte of memory on each one, and it's cheap, and now you can scale 10 times further. By the time you scale there, generally, you're going to be able to buy upgrades for about the same price as you did before, and you're just going to be able to scale diagonally. And it's much easier to scale that way. It may not be the cheapest way, but it's not very expensive either. So moving on a little bit from the database, another big bottleneck is when you're doing all these denormalized things, you're writing all this data to different views, to different caches, certain things can become slow. If we need a counter of everybody in this room, and we have thousands and thousands of these rooms, we don't need the counter in real time, we want it close to real time, but we can't do thousands and thousands of writes as soon as everything changes. So what we do is we build an asynchronous task, and we do that with queuing. So here's an example of why this is a problem. To write to all of our views, we're going to have the public timeline, we're going to have the timeline of people that you're interested in, and we're going to have the timeline of just you. So we're going to write to 3 views, and that's those 3 views rather. However, once you post a tweet, and if you have a lot of followers, we have to write to every single one of their streams. And if you have 100 followers, that's 100 writes. If you have 1 million followers, that's 1 million writes. You can't do that all in the process because it just gets too slow. So we generally we use Rabbit, we use Celery, and a little bit of our own HackerSquid implementation. And we do fan out, and we've actually built a nice delayed signal system. So we have application triggers everywhere. We don't use any database triggers. And as soon as something is saved, if it's something we've dubbed interesting, it gets treated as this delayed signal, which is sent out to Celery workers, and then it's split out into subtasks, basically. And then it can basically just fan out the jobs, and different delayed signals can connect, just like if they were using a Python dispatcher or something. Again, the example of if you have a lot of followers and you tweet, it's going to be a big problem. This is Ashton Kutcher's profile, and he has 7 million followers. So every time he tweets, it has to be written to 7 million strings. And to scale this, again, you need something like a queue. And you need a synchronous task that you can say, I've created a tweet, now I need to send this task, and however many machines I have, I could have 7 million machines, and they could all write it instantly. So you're not sacrificing the real-time aspect by doing things like this. This is more or less a cache, but it's using new shiny NoSQL data stores, which have awesome data structures and awesome functionality. So again, we're using Celery to do this. Celery with Django is awesome and easy to set up. You drop in Django Celery, which will have the dependency on the actual Celery package, and then on your workers, all you do is run the Celery daemon, and it'll just open requests and kind of works. So going back, this is what our post save look like for when a tweet is created. Passes in the tweet instance, and then we write it to all the strings. So once we move to Celery, it's actually really easy. All we do is wrap it in tasks, and we actually have to define a little bit differently how we pass arguments to it because it's serializing. I believe it serializes to pickle. It could be JSON, I don't actually remember. Which means we're just going to pass it as dict. And to cheat, and to fit this in one slide, we're just going to take all of the values in the class dict, and we're going to cheat and reinstantiate it and apply all those values. So given that, we still have a single task here, but you can potentially see how you could fan this out into a bunch of machines and register a lot of tasks. And we're just adding this tweet to everyone's stream that they follow. So let's just say we have our home view, which shows all the people we're interested in. This might be how it looks. 10% of the time, they just fail, which shows really shiny graphic. And then we have our API that we built for the following timeline, and we get the IDs of the tweets, we list those out. Then we actually pull the objects from the database itself by a primary key lookup, which is very, very fast. This gives us a lot of leeway, and we don't have to worry about those caching nightmares that I was talking about earlier. Given that, now we have the IDs, we have the results, we actually need to reorder those so they're in the same order, so we just iterate through and try to append the tweets in the list. There's also cases that you'll find that you lose integrity because you no longer have consistency when you don't have a relational database. So you might have things that somehow are in your Redis cache, but they're not in your database, or they're in your database and not in your Redis cache. Luckily, we don't care about the ones that aren't in the cache but are in the database. We care about the other ones. So what we need to do is we need to keep in mind that the results we're pulling in may not exist anymore. So we may not actually get 100 results back. And if we need 100, then you actually have to repeatedly query until you get those 100 results. And generally, the way we do it is we page through. So if we need 100 results, we pull in 100. If there's 95 there, we pull in another 100. 100 is a small number. It's not very costly. It kind of ensures that if we just try to pull in 5 results, maybe we have to query in, and that's more costly than pulling in 100 results. So I want to talk about why an API is important. A lot of people talk about APIs, and I don't presume to have any idea how to build great APIs. But I can tell you why they're important, and why they're important for scaling your code, for scaling your architecture. And these are kind of the APIs that we're using here. And they all kind of access the same kind of data. So we have our list method on the timeline. We run a z-range query, which is it's a query that says, give me the data from this list, give me back end results, and they're sorted. We also have this tweet.objects.all, which in Django is just the ORM that says, give me tweets from the database. And then let's say we have a RESTful API. All of these are actually the exact same data that's being returned, so they can be all in the exact same API. And if they're all in the exact same API, that means if we have some easy way, let's just say we didn't have materialized views and we were just doing tweet.objects.all, so we were querying the database, but they're all in some API, we introduce materialized views, we drop them in, everything is faster. So we've made the system scale and perform much easier by just changing one single point. So let's go back and let's refactor a little bit of the code. Originally we were getting the tweet IDs. Sure it works, but it's generally not what you want. And being dry, we don't want to have to repeat ourselves, so we want to actually refactor this so we actually just get tweets back. And given that, it makes it much easier to have a consistent API. So we changed this, and we're going to expect tweets instead of tweet IDs. We moved that logic that we were doing before, pulling the things from the database, setting them in a dictionary, and then returning the results into the list method. So now we're returning tweets instead of tweet IDs. Now, what we have here is a nice cache on top of our database, which is kind of a cache. It's Redis, it's not entirely a cache. And so we can add a cache on top of that. So basically, I tried to simplify this as much as possible. I hope this makes sense. We pull in the objects from the database, or we actually pull in the objects instead of from the database from a cache key. And I was told last night there's actually a better command for this in Redis. There's like a multi-git, like git many in memcache. So we pull in every single object, one key at a time from Redis. And the object could be like a serialized tweet, or it could be a dictionary of the values you need, or it could be a fully rendered state. Now what we do is we say if there are any objects that return a none result, because every single object here is mapped by the key and then by the value, so it's just a dictionary mapping. If any of those are empty, we actually need to query the database for this. So we only query those ones that we're missing from the cache, and then we actually serialize those back into the cache. So there's only one miss here, ideally. And then, so now we've sent each of these values back in the cache, and we just return them like we did before. And this makes it really easy, because now, if that tweet changed, if it got deleted, if the message changed, if for whatever reason the author changed, all we have to do is update that one value in the cache, and the representation of that object is the same everywhere. And it makes it really nice when you need to moderate data, and you have all these caches. If it's a miss and it's been moderated, you just query for it again, and if it doesn't match the original conditions, if it's been deleted, or if it has a flag that says it's been deleted, it no longer gets returned as part of that cache. And it makes it very, very easy to have a real-time distributed system that performs very, very well, and also has the capability to remove data very quickly. So we're breaking this down a little bit more, and I just kind of went through this. But the first thing, again, we're storing each object in its own individual key, which, again, makes it easy to invalidate, easy to push state. We hit the database for misses. We just do a primary key in list of missing IDs. And then we store those misses back in the cache, and then we use a little functional-ish programming to filter out the misses, or filter out misses from the database. So I talked about how we can push back into the cache. And it actually is very easy when you have a system like this. So we had this add method, which would add to our cache before. And you can factor this out even further if you're using like a signal dispatcher, which Django has. And you can just connect to like a post-state hook and immediately push everything back into the cache without having to explicitly say add to timeline. So in this case, as soon as we add, we actually push it. We push the object into the cache and we push it into the list, which means it's always there as soon as it hits the list, which means there's never a miss. And there's never a miss because Redis doesn't implicitly have expires. You can set expires on keys, which you may want to, but if you're pushing state, you generally don't need expires unless you're concerned about any of those push mechanisms failing and the data being stale for long periods of time. Removing is also really nice now. We remove it from the list first because it's very important that it's removed from the list first, added to the list last. That way it's in the cache and removed from the cache. First in, last out. Yeah. And so yeah, we just remove it from the list and then we remove the actual object from the data itself. And again, you could improve this even more by making, so these keys are keyed to the class itself. So they're keyed to the public timeline right here. And one step further would actually be to make these generic keys, so it's just a generic object cache. So all of the objects are shared by every timeline. And if I have this tweet by Ashton Kutcher and this tweet by Arnold Schwarzenegger and everything, they're the same everywhere. The objects are the same everywhere. Their representation is always the same, which again goes back to managing your code, managing the cache, and invalidating. So to wrap everything up, hope I'm not too bad on time. Okay. So use a Cramer, and I really mean use a Cramer. There's no reason not to. Don't roll your own. Django, Flask, Pyramid, they're all really great. They all have different levels of complexity. Django gives you pretty much everything. Flask lets you do whatever you want. Pyramid is more about, it lets you have the ability to do a lot of things, but there's also pylons that I think is going to be running on top of Pyramid soon, which is another choice. It's very simple. So in this example, we started with the bare basics in our schema, which worked just fine. They scaled just fine. We started with very simple solutions. The materialized views, we iterated through how we could build this out as a product. It wouldn't have to be in one iteration. Like, we can start off with just querying the database, then we can start off with the materialized view, and then we can start off with caching within that materialized view. And like ideally, that caching would probably be in Memcache and not Redis. And then we handled invalidating and pushing objects to the cache because now our data scale has grown to be much harder to manage. Scale generally leads directly to performance. It doesn't go the other way, which I think is why a lot of the confusion between the two words. They tend to get blended together, and I think there's good reason that they do, but they're not the same. And consolidate the entry points through some kind of common API, whether it's RESTful API, backend API. For example, Twitter, ourselves included, we actually power almost everything off of a RESTful web service. It's almost like building procedures, and once you get to a large infrastructure, maybe you don't need, but you probably should go service-oriented, which means anything that touches the database is this service over here, which means updating that is very simple. You just maintain compatibility. Anything that touches the web API is this service over here, and it communicates through the database API. And then anything that's showing on the front end communicates through the web API. And this makes it very, very easy to scale out your deployments, your data, to do upgrades, to do all these kind of like really nice things. And when you have those entry points that are very isolated, it makes it very easy to optimize, to improve performance, to improve scale, just a general manageable architecture and code base. And so then, like, let's look back on some things that, I guess some lessons learned. So I think when we started with Redis, we started with an analytics product. We also tried Hadoop and HBase and some other things, and they didn't work too well for our needs. And we started with a low number of shards. And again, we're planning ahead here. We're not planning to scale enormously, but it's easy to run 64 VMs, even if we're never ever going to need 64 physical machines. So if we have more up front, it's going to be easy to scale if we ever need to. Rebalancing shards is a nightmare. It means you have to pull in all the data. It means you need, I think, like 3x the number of machines, or the number of instances at least, to actually rebalance that data, because they need to be pulled into some kind of central source. They need redistributed among everything, but you don't want to suffer downtime while you're redistributing, so that entire cluster has to be up. The failover for that entire cluster needs to be up. And then we need everything else, which ideally is 2 more clusters that will be the new replicas that are going to be put into place. So it's not something you ever want to have to deal with. Eventually you probably will if you get really, really big, but you can plan very, very far ahead. So push the caches and don't pull. Like a lot of examples I always see is, I want to query the tweets, so I fetch from the cache. If it's not there, then I query from the database and I write it to the cache. It works, and there's ways to deal with some of the problems. One of the problems is stampeding, which means 5,000 users immediately hit that expired cache key, and now they're all pulling from it. There's ways to deal with that, assuming it exists in the cache somewhere. If it doesn't ever exist in the cache, then you're kind of, SOL when those 5,000 users come. They either have to block the request, so they're not all querying for the same data, and that data can be very slow to populate, or they all query for it, and it's a nightmare. So pushing, highly recommend, Memcache is cheap, memory's pretty cheap. Push everything to the cache, let it expire. Like, we have a default expire of 5 minutes on every single thing in our memcache. And surprisingly, we didn't even use memcache that heavily until recently. And we had no issues. Like, Postgres is rock solid. Denormalize the counters and views. And I wanted to go into this a little bit more, but I was realizing that it's becoming too much code and taking too long. So another thing we do is we don't just write the views, but we write counters. We do this for metrics, for analytics, for a lot of various like web products, and we want to know like how many people are in this room, or how many followers you have, or something like that. So again, with this queue system, as soon as something's saved, we update the counters. And we actually do a lot of this in Redis, and it works great. We don't do things like that in memcache just because we want persistence. Also to note is that I don't recommend using any of these solutions, MongoDB, Redis, etc., as your primary data store, because they generally don't work at some point, and then you may lose data. MongoDB has a pretty bad reputation of this. Redis has done okay for us. We don't use disk store, unfortunately, but we ensure that everything can be rebuilt if it needs to be. And then, yeah, again, queue everything. Like, day one, push everything in the queue. It's going to make process time so much faster. You're going to have stuff that's slow that isn't that important. Just push it all into the queue. Celery's too easy to set up to not do it. And I guess some things you can do to improve on this. So I talked a little bit about normalizing the object cache key. So it's one shared object cache among all your timelines in this example. Awesome benefits from that. Just easy ability to invalidate with low write counts. Application triggers. Don't ever use database triggers, please. It's nice because you can do things directly in the database, but we have a lot of data and we don't need to do raw queries. We iterate through enormous amounts of data fast. I think to get through our entire set of posts, which are comments, we have 150 million of those. For example, to fill our search backend, I think it took 8 hours to go through everything. I also wanted to talk about pagination. So if you have problems with pagination, I have some really cool ideas. But there's ways you can do better pagination. Don't use limit offset, especially in SQL. It's slow. It's very, very slow. The reason it's slow is because if you want the first 100, that's easy. It does the query. It has kind of this index built, and it just pops out the first 100. If you want 1,000 to 1,100, it actually has to step through the first 1,000 before it can get to the next 100. And as you get larger and you page further in, that gets slower and slower and slower. And it's not just CPU time, it's a lot of memory overhead too, because that, like, SQL servers have to buffer all this in there. So there's really cool ways you can do pagination. The most common and easiest thing, especially if you're doing like tasks where you need to iterate through everything, is do what I call a range query set. I don't know if there's a technical name for it, and that's literally step through the IDs in chunks. So I do a select where ID is greater than 1,000, less than 1,100. Maybe that gives me 100 results, maybe it doesn't. If I need more, I can do another query that fetches the next 100 IDs. And those are all very fast. They're primary key indexes, amazingly quick to do lookups on. And again, build with the future sharding in mind. Build with the 64 nodes on VMs that are really easy to set up. And don't build 12 shards because you don't think you'll ever need more than that. Just build massive amounts. It's not that hard to maintain. If you're using something repeatable like Puppet or Chef, just set up the Redis nodes, set up the VMs, and set up your configuration, and it just works. And that's about it. So, questions?
Hi, I lost track between sort of Aston Kutcher and the cache misses. Can you go through it again? Like if he tweets something and it goes through, like this writes to the queue 7 million users, and then he, crap, spelling mistake, and he removes it. Wouldn't that make like 7 million cache misses? Or is like?
So if he removes it, let me think about this. If he removes it after it's been written, it would be removed. So it would actually, depending on how you did it, it could still be in the cache, or it could not. It depends on how you want your product to work, I guess. If you're okay with it showing up in the cache and showing in the stream until it's done processing, then yeah, you have no cache misses. You just have to wait for the 7 million additional writes to execute. which may be the preferred way, but maybe you're concerned about like pornography or something like that. So then you're willing to accept that you'll have 7 million cache misses when Ashton Kutcher accidentally posts a photo and needs to delete it or something like that. So it really depends on, I guess, your product requirements.
Questions? Okay, I do have a question.
Okay.
So how would you change your whole strategy if you need to do some real tasks like updates or multiple updates on a single tweet? So that you are updating your data you have a sort of concurrency.
So to make sure you're not, so if multiple people are updating the same thing?
Yeah, you have to update the cache and also the storage. So
yeah, that's a hard problem to solve. We have a lot of issues with integrity like this. So again, we rely on the relational database first. And I think our queue runs basically in order. So hopefully you're passing in the correct data so it gets serialized correctly to the cache and it's in the correct state in the correct order. Yeah, I don't really have any great solutions for dealing with the consistency on that level. It's very painful. Yeah.
Questions? Don't be shy. That's okay. Thank you, David.